Before we talk about the domain of the square root function, I just want to remind ourselves what the square root function even is. So here I've made a graph of the square root function, and along the x-axis I've plotted the numbers 1 to 16, on the y-axis I've got the numbers 1 through 4, and then in this green curve here I've plotted the square root function. What is the square root? Right? Well, here's an example. Here I've got the square root of 4, and I'm saying the square root of 4 is 2. What that means is that if I take the number 2 and I square it, I get back 4. And or if I move over to, say, the square root of 9, I get 3, and that's because 3 squared is 9. Right? Or if I move over a little bit further, the square root of 16 is 4, and that's because 4 squared is 16. And there's some crazier values too. If I move over here to the square root of 2, well, the square root of 2 is this sort of crazy number, 1.414213, blah, blah, blah. And maybe it's a little bit surprising that if I take that number and square it, I get back 2. So what's going on here, right? The square root function takes a number and spits out a new number. That new number, when you multiply it by itself, when you square it, you get back your original number. Now, here's the question. What sorts of numbers can I take the square root of? That's asking the question, what's the domain of the square root function? Now that we've seen the graph, let's try to write down in words a definition of the square root function. So in light of what we just seen, you might think that the definition of the function f of x equals square root of x is a number which squares to x. There's a problem with this, though. Take a look at, say, f of 9. What would f of 9 be? Well, if you're thinking the square root of x is a number which squares to x, then you might think that f of 9 would be minus 3, right? Because minus 3 squared is 9. But then you might also think that f of 9 should be 3, right? Because 3 squared is also 9. This is bad, right? A function's supposed to be unambiguous. It's supposed to have one output for each input. If you take this as the definition of the square root function, just any number which squares to x, you've introduced some ambiguity, right? What's the square root of 9? Is it minus 3 or is it positive 3? Both of those numbers square to 9. So this is bad, right? The solution is to change the definition. Instead of having the square root function be just a number which squares to x, you're going to take it be the non-negative number which squares to x. This is better, right? In our example here, if I only am allowed to choose the non-negative number which squares to x, then f of 9 equals minus 3. Well, minus 3 is not non-negative. Minus 3 is negative. So that means that this isn't the case, right? All I'm left with is f of 9 equals 3. Right? 3 is the non-negative number which squares to 9. All right, so this will be our definition for the square root function. The square root of x is the non-negative number which squares to x. There's one particular place where this plays out that's extraordinarily important. So let's take a look at that now. We've got our definition. The square root of x is the non-negative number which squares to x. Now, there's one popular misconception that comes up because of this definition. So in light of the definition of the square root, right, the square root of a number being the non-negative number which squares to the number of the radical, you might be tricked into thinking that the square root of x squared is x. That's not true. Let's see why. Let's do a specific example where, say, x is minus 4. So if I replace the x's here by minus 4, the left-hand side is the square root of minus 4 squared. Right? The square root of x squared, but with x replaced by minus 4. Now, minus 4 times minus 4 is 16. This is the square root of 16. And the square root of 16, the definition of the square root is the non-negative number which squares to 16. There's two numbers that square to 16, plus 4 and minus 4. But the square root is, by convention, the non-negative one. So this is equal to 4. Duh! Look at what happened. Minus 4 square root of minus 4 squared plus 4. That's the x over here. this is not true, right? You should not be tricked into thinking that that's the case. Instead, something else is true, right? What is true is this. The square root of x squared is the absolute value of x. And that works in this specific case, right? When x is minus 4, the square root of minus 4 squared, square root of 16 is 4, and 4 really is the absolute value of minus 4. All right, so this is a mistake that comes up quite a bit. People are often tricked into thinking that the square root of x squared is just x, right? They're just trying to cancel the square roots and the squaring. That's not possible. Instead, what is true is the square root of x squared is the absolute value of x. So we've got a definition of the square root function, and we've seen that the square root of x squared is not just x, it's the absolute value of x. Now, that doesn't actually address the original question, right? The original question is, what's the domain of this square root function? What sorts of numbers can I take the square root of? For instance, can I take the square root of a negative number? Well, let's see why not. Very concretely, does it make sense, say, to talk about the square root of minus 16? Well, if it did, that'd be some number. So I'll call that number k for crazy, right? And what do I know about that number k? Well, k squared would have to be minus 16. Remember the definition of the square root function? It's a number that I square to get back the original number. So if there were a square root of minus 16, when I square it, I'd get back minus 16. I'm imagining here that k is some real number. And that means there's three possibilities. Either k is positive, k is 0, or k is negative. If k is positive, then k squared would also be positive. It's a positive number times a positive number, still positive. But that can't be, because k squared is supposed to be minus 16. So this first possibility doesn't happen. Now, if k were 0, then k squared would be 0, but k squared is supposed to be minus 16, so k isn't 0. Is k negative? Well, then what's k squared? That'd be a negative number times a negative number, and that would still be positive. And that can't be because k squared is supposed to be minus 16. So this possibility also doesn't happen. Oh, all of our possibilities have been eliminated, right? There can't be a real number k, which is the square root of minus 16, because if k were positive, k squared would be positive, but k squared has to be negative. K can't be 0, because then k squared isn't negative, and k can't be negative, because then k squared is positive, but k squared is supposed to be negative. Right? Now, the upshot is that it just doesn't make any sense to talk about the square root of a negative number. In contrast, it does make sense to talk about the square root of 0, which is just 0, the 0 squared is 0. And it also makes sense to talk about the square root of positive numbers. So to summarize the situation, we can say that the domain of the square root function is all the numbers between 0 and infinity, including 0, so I'm using the square bracket, but of course not including infinity, because infinity is not a number. Sometimes you're asked to calculate the domain of a function that's more complicated than just square root of x. Let's see an example of that. So let's try this. Let's try to find the domain of this function g, which is the square root of 2x plus 4. And remember, the domain consists of all the inputs for which the rule makes sense. So I just have to think, which x values make sense for this rule? Well, in order to take the square root of 2x plus 4, I'm going to need that 2x plus 4 is not negative. Because I can't take the square root of a negative number, so I need to guarantee that 2x plus 4 is not negative, meaning greater than or equal to 0. Now I can subtract 4 from both sides, and I get that 2x is at least minus 4. Then I can divide both sides by 2. 2 is positive, so it doesn't change the inequality. X is bigger than or equal to minus 2. So as long as x is at least negative 2, then 2x plus 4 is at least 0, which means it makes sense to take the square root. So I can summarize the situation. The domain of g consists of all numbers greater than or equal to minus 2. This is our notation for that. I use the square bracket to include the minus 2 and the round bracket here on the infinity because infinity is not a number. It's not part of the domain. So that example was a little bit harder. Let's do an even harder example where I've got multiple square roots. All right, the square root of something plus the square root of something. Now let's figure out the domain of this function that has two separate square roots. This is the function t of x equals the square root of 1 minus x plus the square root of 1 plus x. Now, in order for this rule to make sense, I have to be able to take this square root and also take this square root. In other words, in order to do this first square root, I'm going to need that 1 minus x is bigger than or equal to 0. Right? I need the thing under the square root to be non-negative in order to take the square root. In order to take this square root, I need 1 plus x to be bigger than or equal to 0. And both of these things have to be true in order to take both of these square roots and then add them together. So I'll put an and between them. Now, I could add x to both sides in this inequality, and I get 1 is bigger than or equal to x. And I could subtract 1 from both sides of this, and I'll get x is bigger than or equal to minus 1. And again, both of these things have to happen, right? I need x less than 1 and x bigger than or equal to minus 1 in order to evaluate this function. Let me write this in a more reasonable way, right? Instead of writing 1 bigger than or equal to x, I can write what I just said, x less than 1. And here I'll write this as x bigger than or equal to minus 1. Now I could write these inequalities as something about an interval. I could say that x is in the interval minus 1 to 1, right? To say that x is less than 1 and bigger than or equal to minus 1 exactly means that you're inside this interval. And I'm using square brackets here because I've got greater than or equal to, less than or equal to. And then I can summarize the situation by writing the domain of t is this interval. Right? This is describing the values of x for which this rule makes sense. That's the domain of the function t. Let's do one more example. Some square root problem where I've also got an x squared term. Let's calculate the domain of this function c. C of x is the square root of 1 minus x squared. So the domain consists of all the inputs for which the rule makes sense. So I'm looking for which values of x make the thing under the square root non-negative. There's lots of different ways to think about which values of x make this true. One way is to factor 1 minus x squared. So I could factor 1 minus x squared as 1 plus x times 1 minus x, right? That is equal to 1 minus x squared. I'm looking for when that's non-negative. This is a little bit easier to think about because now I just have to figure out when these two terms have the same sign, right? When they're both positive or both negative, then their product is bigger than or equal to 0. So to think about that, I'll draw a number line, and I'll first think about when 1 plus x is positive and negative. So something special happens at minus 1. Right? When x is minus 1, 1 plus x is 0. When x is less than minus 1, 1 plus x is negative. And when x is bigger than minus 1, 1 plus x is positive. All right, now compare this with 1 minus x. Right? 1 minus x, something exciting happens at 1. Right? When x is less than 1, 1 minus x is positive. And when x is bigger than 1, 1 minus x is negative. Now, I'm not trying to really understand 1 plus x or 1 minus x. I'm trying to understand their product. So when I multiply those two together, I get 1 minus x squared. And I want to know, when is that positive or negative? Let me mark down the special points minus 1 and 1. And now 1 minus x squared is the product of these, so I can think about various values of x. So when x is less than minus 1, then 1 plus x is negative and 1 minus x is positive, and a negative number times a positive number is negative. When x is between minus 1 and 1, then 1 plus x is positive and 1 minus x is also positive in that region. So their product is positive. And when x is bigger than 1, 1 plus x is positive and 1 minus x is negative, so their product is negative. Now this gets me most of the way there, right? Because what I'm trying to understand is when this product is non-negative, and I can see that it's positive in this region. I can also think about what happens when I plug in minus 1 and 1. When I plug in minus 1, I get 1 minus 1, which is 0. When I plug in 1, I get 1 minus 1, which is 0. So the function's in fact 0 in between here at minus 1 and 1. So I'm just trying to figure out which values of x make 1 minus x squared non-negative. Well, minus 1, 1, and anything in between. So one way to summarize the situation is to say that the domain of my function c consists of all real numbers between minus 1 and 1, including minus 1 and 1. So I'm using the square brackets. And as long as x is inside here, then 1 minus x squared is non-negative. That means it makes sense to take the square root. And that's the domain of C.